lecture. Okay, so last time in the last lecture, I spent too much time to derive the details. So yeah, sometimes lecture is something like that. But hopefully we can keep up with the more advanced ingredient. The standard model, let me just start out with the basic structure of the standard model. And then today we are going to discuss standard model and spontaneous symmetry breaking. I think spontaneous symmetry breaking includes Goldstone theorem and Higgs mechanism. So Goldstone theorem for global symmetry, Higgs mechanism for local symmetry. The standard model Lagrangian standard model structure will be we need to consider a standard model gauge group as a product of three independent local gauge group. So these are local gauge symmetry. So for SU3, so SU3 we are actually for SUN there is in the dimensional group, so-called dimensional group equal to n square minus 1. So if you consider a transformation matrix on the SUN, you have n square minus 1, so independent degrees of freedom, independent transformation matrices. So because of that, so SU3, 3 square minus 1, which is 8, right? So then you need to include gluon associated with each transformation. So this lambda A, so-called lambda A equal 1, 2, 3, There's eight of them, and associated gauge field will be gluons. And so in the case of SU3, 2 square minus 1, therefore there are 3. And we have, let me write this. The Pauli matrices will be transformation matrix. So I run over 1 and 2, 1, 2, and 3. And the associated gauge field W, I mu, those are weak gauge bosons. And then U1 factor, just the 1. And that is just the hypercharge operator. So there's a charge operator, hypercharge. So these are, so if you have only one charged particle, you don't have to introduce charge operator. But if you have a multiple of them, you could have different charges under the hypercharge. So, and then associated gauge boson, hypercharge gauge boson. So in order to make the gauge invariance, in order to make the gauge in respect the gauge symmetry, gauge invariance. As we discussed, let's say all the derivative must be changed to covariant derivative. So we need to introduce covariant derivative for the standard model gauge symmetry G. So round mu minus strong first, strong interaction. Then you have a gauge field. And so lambda A, actually, so this lambda matrix is about Gell-Mann matrix, 8 of them. And this tau is Pauli matrix is 3 of them. And so I need to divide by 2 here in order to make the generators to satisfy the commutation relation. So I will talk about that too. G, and then weak gauge version. Again, there's a 2 here, factor 2, and minus hypercharge. I hypercharge and mu gauge field. And so this psi is a matter. So all the matter and Higgs also. Higgs scalar also included. So, and then the form of the matrices, so depends on the representations. So those, just here, you have just independent matrices, but the representation, the precise form of the matrices depends on the representations. So in the standard model, we have kind of fundamental representations. So those are kind of fundamental in fundamental representation of SU2. SU3 cross SU2 cross U1. So fundamental, the kind of a minimal representation. Okay, so, and also commutators, as we discussed, Lie algebra, so Lie group. By definition, when the generators here, in the case of SU3, this Gell-Mann matrices is in the case of SU2, Pauli matrices, the number of generators depend on the group, and those satisfies kind of universal algebra. This one, and this group structure constant. That's gauge group dependent. So that's group dependent. So in the case of SU2, as we discussed, this group structure constant is just nothing but epsilon ijk. So Levi-Civita symbol. So 1 or -1. But in the case of SU3, it's more complicated. So you can check this more explicitly. So it's not epsilon ijk. So some numbers. It depends on the indices. But the thing is that in general, this totally fully anti-symmetric. So if you change indices, if you change pair, interchange the pair of indices, then you will get a minus sign. So this is the universal structure, and only if you take this one, the gamma matrix is this. I mean, this sorry, not gamma matrix is the Gelman matrix is more explicitly the SU2. In the case of SU2, let me give you a simple representation. Okay, the form of the representation. Actually, there are two. For in the case of non-abelian, in general non-abelian gauge symmetry, there are two simple representation. One is fundamental, and then simple and useful. Fundamental representation, and also other joint representations. So these two are important, and the fundamental representation is like the quarks and lepton, etc. Right? Those are, and Higgs also. So those are in the fundamental representation. In the case of us joint, these are gluon, and those are gluons and weak gauge bosons. Those are other joint representations. So the gauge forces are other joint representations. So that takes a particular form of the matrices. And so I think for instance, the other joint representation is the T. So let's say I, J, K equal to I, L, I, K, for instance. So these are, as you can see, IJ runs, I, J, K runs 1, 2, dimension of G. So this is pretty general. The dimension of group, you can count depending on the group, and then just because of that, this Ti, in this case, transformation matrix will be dimension G times dimension G. Okay, so that is the kind of a dimension G times dimension G. So in the case of gluon, so 8 times 8. In the case of weak gauge bosons, 3 by 3. So that is the joint representation. And you can check explicitly this form of the representation satisfies Lie algebra. So one of the problems, I think the last problem of today was to show the is to show the Jacobi identity. And Jacobi identity, actually, if you take this representation, Jacobi identity is nothing but the Lie algebra for the other joint representation. So maybe in words, it's not that clear to you, but I think that this is the most actually natural candidate for the transformation. And the fundamental representation is that in the case of fundamental representation, in the case of SUN, we call N or N bar. Okay, those are fundamental representation. So there's the N component. Okay, so let's say this, if this psi is N fundamental representation, there should be N component, 1, 2, something like that, right? So in, for instance, SU3 color, then we need to have, let's say, up quark maybe of course we have a left-handed or right-handed, and then there are three components. So 1, 2, and 3. So this short-handed, and then A is a run over 1 and 2, 3, 1, 2, 3 is a color index. This I is a color index. So in the case of SU2 left-handed, we are mixing between different flavors. So let's say quark, doublet, left-handed, U, L, and D, L. And of course, it carries some color index. Each, up or down quark, they also carry color index. But not only that, this also, so you can write down, maybe in principle, this, you can put the color index for the doublet as a whole. And this doublet, quark doublet, has also another index, I. So I stands for U or down, up or down. So there are two indexes in the case of in the case of quark doublet, right? So in this case, of course, A 1 and 2, 3, but these are hidden. Let's say it's hidden on because of SU3, we are dealing with it separately. So I equal to 1 and 2. So those are SU2 fundamental representation. Okay. So I think that is clear. Then the fundamental representation, if you fix the number of component, then automatically you can see that in the case of SU3, the Gamma matrix must be 3 by 3 because you are changing 3-component object to 3-component, another 3-component object by rotations, transformation. So because of the transformation matrix must be 3 by 3. And also in the case of SU2, the Pauli matrix must be 2 by 2. Of course, we know that the Pauli matrix is 2 by 2. But the SU2, in general, transformation matrix for SU2 can be multidimensional. It's more than 2. If you think of higher dimensional representation, because it is a minimal, it's a fundamental. Because of that, we are considering 2 by 2, but it could be 3 by 3, or 4 by 4, etc., etc. So, but these are minimal in the sense, yeah. So in the sense, so because of the fundamental representation, the transformation matrices fundamental representation, of course, in the case of SU2, there are 3. T 1 equal to tau 1 over 2. Okay, so, and this tau 1 equal to 0, 1, 1, 0, usual Pauli matrix. So 0 minus I, 0, and tau 3 equal to 1, 0, 0, minus 1. So in the case of SU3, now fundamental. So fundamental in the sense that you are considering field transforming as the fundamental representation, like a quarks. Yes. So, and so then you need to consider. So let me put indexes. I put label A instead of I. Oops. A. Okay. There are 8 of them. And those are Gell-Mann matrices, as I said. And this Gell-Mann matrices contains 8 of them. And you can find this explicit form of matrix in the textbook on that too. So if you the first 3 is very similar to the Pauli matrices. So the reason is that this SU3 contains SU2, although it does not contain SU2 left-handed, but in the sense SU2 color. So SU2 color contained in SU3 as a subgroup. Because of that, the generators, even if the generators matrices, we call generators, transformation matrices generators. Even if the generators are 3-dimensional, 3 by 3, it contains 2 by 2 matrices, a subgroup, sub matrices. So lambda 3, you can guess. So -1, -1, 0, 0. Right, this one. So those are SU2 color subgroup. So if you rotate quarks by these 3 of them, then just you can define SU2 color subgroup. There are more than that, right? And then there's the lambda 4, 0, 0, 0, 0, 0, 0, 1, 0, 0. So this one minus this 1, and lambda 5, 0, 0, I, 0, 0, 0, I, 0, 0. You can see that in the case of lambda 1, 2, 3, you have a Pauli matrices in the first 2 indices. So 2 by 2 kind of block. 2 by 2 block, you have a Pauli matrices. But here, so you can also take notice that 1, 1 in the 1 and 3, or 3 or 3, 3, 1 and 3, and the other entries are 0, and also I and minus I. So it has the similar structure as the first 2 Pauli matrices. And then let me continue to discuss 6, 0, 0, 0, 0, 0, 1, 1, 7. So now you can see instead you have in the last 2 indices, you have a block, 2 by 2 block, which is which are the first 2 Pauli matrices. And the last matrix is non-trivial, 1, 1, minus 2, 0, 0, 0, 0, 0, 0. Okay. So, and then I think from the explicit form of the generators, as you can see, all the generators satisfy certain conditions. So from there, all the matrices Hermitian and trace of generator vanish in both SU2 and SU3. So these are traceless, and then this Hermitian. Traceless, okay. So those are a general property. So those are general property. Property of what? SUN. And one more thing, I think I also taught some group theory for undergraduate mathematical physics. So in the undergraduate mathematical physics, it was noticed also, although you are not introducing on more matrices, but if you take the certain linear combination of the already introduced matrices, so if you take this combination, then for 1 and 3 indices, you have a SU2 subgroup. So similarly, if you take the linear combination of the sum of the matrix lambda 8 plus lambda 3, then you have 2 and 3 indices. You can define another SU2 transformation. So in group theory, why this important lambda 3 and lambda 8? Because it is diagonal. So it is diagonal. So if you look at the diagonalized, so other matrices are not diagonalized, but in particular this one, okay, and this one is a diagonal. So 1, -1, 0, right? And this lambda A is 1, 1, -2. So because of that, this lambda 3 is the so-called Cartan subgroup. So let me call this H Cartan subgroup that belong to the big group SU 3 color. The Cartan subgroup. So commuting. So-called the number of commuting generators equal to the rank of group. Because of that, SU2, SU3 so has rank 2. So group theory is the rank is very important. So when you consider the spontaneous breaking of non-abelian symmetry, the rank is very important. So just to leave it here, and then also lambda 3 and lambda 8 is an implication. But let me I'm spending too much time, so let me go on to discuss again the standard model meta content, and then spontaneous breaking. Okay, so Q standard model meta content. So representation. So Q quark doublet. First quarks. So quarks is quark doublet UL TL. So let me ignore the color indexes, okay? So we call, this is the 3, 2, and plus 1/6 is in the subscript. So 3 stands for SU3 color. So 3-dimensional representation on the SU3. And the second entry 2 is the fundamental representation under the SU2. And this hypercharge. The 1/6 is hypercharge, okay? So then the right-handed quark, up-type right-handed quark also can be denoted in this form, right? So again, the 3, SU3 color does not distinguish between left-handed and right-handed. So they transform in the same way, left-handed and right-handed. But the left-handed and right-handed, they transform differently under the SU2. So there is no pair. There is no SU2 partner for right-handed. So they transform. So one is null transformation. And then down quark, dr equal to 3, 1, 3, 1 minus 1/3. So here, how to get this hypercharge. So those hypercharge kind of introduced in order to define to get electromagnetic charge. We assign the hypercharge depending on the representation under the SU2. So this Pauli matrix, third component, Pauli matrix is in this form, diagonal form, right? It's 2. So because of that, for instance, UL charge, UL charge is a diagonal. So T3 is a diagonal. So you can say that so left-handed up-type quark carry 1/2 charge under the SU2, the part of the SU2. So 1/2, so 1/2. Because of, and then hypercharge, you need to determine the hypercharge must be the same for U and D, because the hypercharge commute with SU2. So SU2 hypercharge, they are independent. Because of that, U left-handed, down D left-handed, they carry the same hypercharge. And we know that the hypercharge for U up-type quark, so the electromagnetic charge type quark must be 2/3. Because of that, you can see this is 1/6. So that's how you can determine the hypercharge. So the same is true for dl equal to Q equal to now. So SU2 charge for down type quark will be minus 1/2, and then this one. And we have already determined the hypercharge for doublet quark. So you see that this is the what is this? Minus 1/3. So similarly, right-handed of quark doesn't transform under the SU2. So just to T3 is just you don't count. So T3, no, there's nothing. So hypercharge one. Hypercharge, that is the hypercharge right-handed. The electromagnetic charge. So my fan is breaking. So that's how you get 2/3 right-handed, up-type right-handed. They are same is true. This is the minus. This is how you got this, the quantum numbers. So similarly, you can also actually the Weinberg model. The Weinberg model is the model of leptons. It's not quarks. At the time, we don't know about quarks much. So because of that, the Weinberg we like to weak theory of Weinberg's is a model called the model of leptons. So it started from leptons, and the lepton neutrino electron. This is the 1, 2, and 1/2. So here is a null transformation. So as we discussed before, so in the case of right-handed, it does not transform under the SU2, but in the case of lepton does not transform under the SU3. The hypercharge you can determine similarly. So neutrino Q T3 plus hypercharge lepton. So the neutrino is neutral, and the hypercharge is so it is on the upper entry. So it carries 1/2 charge, electroweak charge, and the hypercharge for the lepton doubly must be 1 minus 1/2. Similarly, you can find the consistency for the left-handed electron, which is charge -1, and with the minus 1/2 hypercharge, and the electroweak weak charge minus 1/2. So you got -1. So you got actually the consistent kind of charge assignment for every particle in the standard model. And also electron right-handed, 1 minus 1. So it's a very dull object, electron right-handed. It doesn't transform under the SU3. It doesn't transform under the SU2, but it has the hypercharge -1. So you can also check explicitly. Just in this case, hypercharge for the right-handed electron is the same as electromagnetic charge of electron. And Higgs also double it, pi plus pi 0. So we call this 1, 2 plus 1/2. So these are the upper entry is the charged, and the down entry is the neutral. There is a charged scala and neutral scala under the electromagnetism. And you can convince yourself of this assignment, charges hypercharge assignment for Higgs doublet. So we call this as Higgs doublet because of that. And the quarks also doublet, also singlet. So it's a singlet, this is a singlet. SU2 singlet. So in the sense of SU2. And in the case of Higgs representation, you can take the complex conjugate and multiply by second Pauli matrix tau2. You get phi 0 star minus phi plus star, which is again in the same representation under the SU2. So SU2, in the case of SU2, 2 bar equal to 2. So 2 actually bar representation is a complex conjugation. So this is a complex. So complex conjugation is the same as 2 and 2 bar, 2 bar is the same. And then the only difference is the hypercharge. Hypercharge changes signs. So I think there is 2 ways of writing down the Higgs doublet. Okay, we have some minutes to discuss. So there are some, I want to discuss phenomenology for the Weinberg angle, Weinberg-Salon model after that. But let me spend more time on the spontaneous symmetry breaking. So let me motivate you why we are considering spontaneous symmetry breaking first, and then we are going to discuss spontaneous symmetry breaking for global symmetry and the spontaneous symmetry breaking for gauge symmetry. So first, I will motivate you why do we care about symmetry breaking in the first place, and then discuss spontaneous symmetry breaking. Okay, do you have any question? I forgot to tell you about the gauge group, general gauge group, but yeah, I will discuss more on that. Actually, so SUN is very particular. So at the time of the constructing the standard model in history, there are several attempts other than SU2 cross U1 for the electroweak theory. So SO3 instead of SU2, you could think of different type of gauge groups. So mathematically, there are actually good candidates, but experimentally, this SU2 cross U1 is favored, and the other candidates are ruled out. Because of that, I want to say that there are competitive models in the past, and for constructing BSM models, it is important to know what other different candidates for the gauge theories are. So I will tell you more about the general gauge, non-abelian gauge groups briefly, and then I will talk about the spontaneous symmetry breaking. Do you have any question?
Yes, I have a question.
Mm.
I don't know what is the hypercharge means and what does hypercharge indicate, and why it is 1/6 for quarks or -1/2 for leptons, and how do we calculate the number?
Hypercharge.
Yes.
Okay. So actually, this identification for the electromagnetic charge, it is from the breaking of SU2 cross U1 hypercharge to electromagnetism. So that has to do with the spontaneous symmetry breaking. And the charge operator for electromagnetism, Q, this is charge operator, Q is written as a linear combination of T3. So T3 belongs to SU3, right? And the hypercharge, this hypercharging. So we take the certain combination. You could take arbitrary linear combination. So T3 actually belongs to SU2. And you can think about U1 part of SU2. Because this U1, the diagonal, and you can think of T3 as kind of U1, another U1 charge operator. And you can take this, the linear combination of two U1 symmetry. So, and then we know how those objects transform on the SU2. So because of that, we can assign the weak charges, 1/2 or 1 minus 1/2. So those are fixed. And then the hypercharge is not fixed yet, but we know what is the electromagnetic charge. The Q is already known. And this T3, if you know the representation, in this case, fundamental, then we know that this is also known. This is known, and the Y can be determined. So this is how we determined. So in the case of UL, it's a 1/2, weak charge 1/2, because it is in the upper entry in the doublet, upper, this one, the upper entry. So this is 1/2, and then Q is a 2/3. So because 2/3 UD, this is the proton, right? This is the proton. Yeah, sorry, not, it's the proton, right? So this is proton. And then UTD is neutron. So because of that, so this is charge +1 and charge neutron. Because of that, you can determine the electromagnetic charge U plus 2/3 down minus 1/3. We know the electromagnetic charges. So they are fractional. So this is 2/3. So that's how you determine the hypercharge for quark doublet. So this is important. So if you want to know, actually Q, electromagnetic interaction is kind of emergent. I mean, in the low energy, you see only this electromagnetic interaction, and this SU2, full SU2 plus U1 is hidden at high energy. You can have an access to these heavy particles if you have sufficient energies. So that's why we are you are matching low energy Q, high energy T plus Y. So this is a very good mathematical structure, and I think there is nothing wrong, and everything is consistent. It's beautiful. I mean, the minimal structure, just from the gauge symmetry. You can we call this embedding. So embedding is the so we find this kind of mathematical structure by comparing with the data. Then this embedding is a good embedding, successful embedding. And then once you know how they are embedded in the gauge theory, then you have predictions, like interactions, how they those particles are interacting with each other. So, more question? Okay, otherwise let's make a pause until 11. So let's start at, and then resume at 11. Okay. Record again. So left-handed, right-handed transform differently. So kind of LR symmetry or parity broken by SU2. Yuan symmetry. You see that the left-handed, right-handed, they transform differently under the SU2, and they transform different, they carry different hypercharges. So apparently left, right symmetry broken. So left-handed, right-handed, as we discussed, this chirality. Oops. So this chirality, it is the same as the helicity for the massless, called the helicity for the massless case. So helicity also important concept. So helicity is the chirality is gamma 5, and the helicity is the we call H equal to this 1/2 spin Pauli matrix sigma and P. P hat is the momentum. Sorry. The unit vector for the unit vector for the momentum. So this H is helicity. So you are measuring the spin along the direction of motion. So when this momentum is here, then spin rotation is this way. Then we right-handed, co-right-handed, and spin rotate different way. Then this is left-handed. So this is a chirality, and the chirality is the same. Sorry, this is helicity, and helicity is the same as chirality. The chirality, as we discussed, chirality, left-handed minus right-handed plus. So left-handed or right-handed here, if you consider Dirac fermion, then upper or lower component, they transform, they carry, they have different eigenvalues, right? So gamma 5, in our case, 4x4 matrix, block 2x2 block diagonal. So because of that, so gamma 5 minus 1 and plus 1. But here, so if you think of the direction of motion along the g direction, because you are free to choose your coordinate. So let's say the direction of motion is the g-axis, then the helicity helicity is just nothing but a third component of the Pauli matrix. So which is the 1/2, 0, 0, minus 1/2. So which is the same as minus 1/2 gamma 5. Sorry, it's not precise, but this is 2x2, sorry. So this is 2x2, so it's not precise, but helicity operator, because it does not contain antiparticle, so it's locally, it's not equality, but the fully, you can define the helicity operator fully for Dirac spinor. But here, let's take the only two-component part, the helicity operator. In any case, in any case, the parity is violated. So let's say right-handed, left-handed here. Okay. The parity is violated because let's say, let's start from right-handed and then applying parity operation. And this spin is kind of angular momentum. It's like this is spin angular momentum, but it's like angular momentum. So under the parity means the x kind of mirror, so it's inversion symmetry. R goes to minus R. So P momentum goes to minus P. And because of that, angular momentum goes to just angular momentum. Both R and P transform, so angular momentum doesn't change. So because of the spin angular momentum, it's just another type of angular momentum, doesn't change under the parity. So that means the direction of motion changes from P to minus P. And the rotation, spin rotation is the same because of that, from the point of view of helicity, so helicity start from helicity 1/2 here, and then the helicity. So this the spin angular momentum is the same, but the momentum direction changes. So helicity flipped. Because of that, we can call this as left-handed. So if the parity is the symmetry of nature, then right-handed, left-handed, you can go from left-handed to right-handed also. Okay, by parity. Because of that, you should not distinguish between left-handed and right-handed. And this parity does not change it, charge. Charge is the same, right? So because of that, if you find, let's say, electron left-handed, you must find electron right-handed by equal amount, and then they must not be distinguished. But we know that this electron belongs to this doublet, right? This one just singlet. Apparently, parity is violated because we cannot transform one to another. So why parity is violated? It's 1956. It's not, Wu is not there yet. So this Li and Yang, they discussed that experimentally the K-ion decays into 2 pion or 3 pions. And we know that the parity of pion equal to -1, called the pseudo-scalar. So parity is defined as the product. So if you have 2 pions, then parity will be +1, and 3 -1. So if parity is kind of a good quantum number, you need to preserve it after the K-ion decaying. But here the parity +1 or -1 both exist. So because of that, it is the first time infer that the penalty is violated. It's not from the electron left-handed or right-handed, but just from the meson decay. So this K-on decay. The K-on is also meson, pseudoscalar. Initially, this every pseudoscalar by definition parity odd. So -1 or parity odd. +1 is parity even. So under the space-time space inversion, R goes to -1. R, this wave function changes the sign. That is the definition. And then 1957, Lee is not Korean, right? Lee is the, what is Lee? Lee is the what is the first name? Lee, Hyun Lee. This Lee is the same Lee, right? So Yang is the Korean name. Those are Chinese, right? So this is T.D. Lee, Xian Yang. Yeah, I forgot the first name, the woman scientist, the experimentalist, who discovered the parity violation. So here, actually this meson decay was the first hint for parity violation. Second hint for parity violation from beta decay. So in experiment, the kind of polarized, the atom has polarized spin in the presence of the external magnetic field, you can polarize spin of atom along a particular direction. So polarized spin. So this is the spin J equal to 5, initial spin. So these are polarized. And then this guy decays into nickel 60. And then plus E electron and neutrino pair. And then nickel carry spin J equal to 4. Because of the spin, because of the angular momentum conservation, these two guys, the spin of these two guys must be opposite. The spin, initial spin direction. And this is the beta decay because one of the neutron and cobalt decays into proton and electron neutrino pair. The origin of this decay is the beta decay of neutron. So so this is the J equal to 5. So J equal to 5 equal to J equal to 4 plus J equal to what I wanted to say. Sorry, the opposite two direction. It's not the sorry. Why am I thinking it's opposite? the parallel. I think they should be parallel. Sorry. So this should be parallel.
So if I remember, because of momentum conservation, electron and the antineutrino should be go to opposite direction for each other, but they have same angular momentum, looks like.
So this cobalt and the 60 cobalt, and then this is the spin direction, initial spin direction, and then okay, yeah. So this is the neutrino, and this is electron. So what I wanted to say is the spin. So let me draw this way. This is the spin of electron and spin of neutrino. Yes. What I wanted to say, I mean, this configuration, so you can, the spin direction must be this way, right? Because the spin angular momentum is the sum of electron spin and neutrino spin. Electron, neutrino, they are spin 1/2, right? So this is up, spin up, those are spin up. And with respect to the initial spin direction. So this is 1/2. So because of that, these two, J is equal to +1. So because of that, after the cobalt decay, the angular momentum is conserved. But the direction of electron could be downward in the opposite direction. I think that it's not spin direction, it's momentum direction. So I'm thinking the opposite direction. You can think of another situation, the electron this way and neutrino this way. And the spin direction should be the same. Okay. Maybe let me see. Okay, I think I now okay, let me see. Okay. So when P 0. Okay, so okay. Yeah, I think this is right. I mean, also you can think of this kind of configuration. Electron, direction of electron is parallel to the initial spin direction, and then spin up and spin up. But for the chirality, things are different in these two configurations. Right? This electron, in this case, the momentum and spin direction is opposite. Because of that, electron chirality is minus, and then neutrino chirality is this guy. I mean, the momentum and spin direction is parallel, so +1, +1/2. And in this case, electron chirality is plus neutrino chirality minus. So if the purity is a good symmetry, you need to see these two events with equal amount. So number of events for the first one and second one must be the same if the parity is a good symmetry, because now I'm telling that the spin, including orbital and angular momentum, total angular momentum transform does not transform under the parity. and also, but the electron momentum changes. Because of that, if you focused on the scalar product of the total angular momentum and momentum of electron, this scalar product transforms under the parity with a minus sign. Because of that, if you take the average of this scalar product, this must be 0. Because you don't distinguish scalar product and minus of the scalar product. Because of the, if you take the scalar product both sides, I mean, if you take the average both sides, then the average must be 0. So the downward electron and upward electron, they will appear with the same number of events. But experimentally, this is not the case. Experimentally, if you define angle with respect to the initial spin direction, the momentum direction, the direction of the electron momentum in this way, then the intensity electron intensity given by this expression, and 1 minus beta E cosine Z. So if electron is relativistic, then this expression approximated minus 1 minus cosine zeta. So because of that, when zeta equal to 0, then this intensity, the number of electrons, goes to 0. On the other hand, if you, so because of that, you can see that this configuration is not observed if electron is relativistic, so almost 0. So because of that, the electron, emitted electron must have chirality minus 1/2. That means the left-handed. And the anti-neutrino, Helest plus 1/2. So this is the right-handed. So because of that, electron must be left-handed, anti-electron must be right-handed. Experimentally, we have this this one. The another indication for the parity violation is from the weak decays. So I think that this one, the beta decay, also a weak interaction, right? So also pion decays. But here, the right-handed neutrino, it does not. This electron right-handed, electron anti-neutrino left-handed does not appear. So if you go back, this configuration. So this one show that this one is electron right-handed. This one is a neutrino left-handed. So those are not observed from the beta decay. So beta decay, the electron, beta decay electron must be, that means left-handed electron, and neutrino must be anti-neutrino must be right-handed. Yeah, it's a little bit complicated. So Wu is the woman scientist, experimentalist who showed this parity violation experimentally. But the Mrs. Wu was not awarded, but the other theorists are awarded the Nobel Prize. So let me give you another example for the parity violation. Parity violation for the from the pion decays. So pions. So if you hit the target by proton, you get produced a lot of pion, and then this pion, positive charged pion decays anti-muon plus neutrino, mu neutrino. And then this neutrino will be the source for neutrino oscillation. And this muon, anti-muon, might be source for G-2 experiment. So this is the typically actually fixed target experiment. And the people observed that measure the chirality of anti-muon. So pion plus here, and this. And this anti-muon spin direction. So this is a spin. You should not be confused with the helicity. So this is a spin direction. Because of the helicity equal to helicity mu1 plus one half. So this is the right-handed. We know that when the spin is up and down because of the Stone-Gallac experiment. So if you measure the spin, then you can infer whether it is right-handed or left-handed. You also know that the direction of muon momentum. So it turns out that the helicity of anti-muon is plus 1/2, so right-handed. And because of the and also this in the case of neutrino will be neutrino helicity is minus 1/2. So this is the neutrino left-handed, and this is the anti-muon, the right-handed. But if you take the charge conjugation, so why do we care about helicity from the first place? It's because helicity is the one commute with the Hamiltonian. So because of that, the helicity is the quantum number, the preserved after, during the decay or scattering processes. But the chirality is not conserved. Chirality is always can be violated by mass term. So chirality is not a good quantum number. But only if the mass can be ignored, you can take the chirality to be a good quantum number. Because initially the helicity Hyun equal to 0. So because of the helicity conservation, the sum of the helicities of neutrino and anti-muon must be equal to 0. Because of that, once you determine the helicity of anti-muon, you can infer the helicity of neutrino in this way. And now we take the charge conjugation of the same process. Then you can see that the plus charged pion changes to negatively charged pion, etc. So then pi minus, and the direction of motion does not change, just charge is flipped. Okay, and because of that, the spin is not sharp, is untouched. So because of that, still you would have mu1 helicity equal to plus 1/2, and anti-neutrino helicity is would be minus 1/2. So that means the mu right-handed and anti-neutrino is left-handed, would be left-handed. So these are weak decays, as I said. The weak decay, the right-handed partner does not participate, but we know that, but forget about weak interaction. If charge conjugation is good symmetry, you must see this decay events as well, but you don't see. We haven't found any evidence for the right-handed mu1 from the weak, from the pion decay. So because of that, charge symmetry, charge is not, charge is conserved, but what I'm saying is charge conjugation. Symmetry is broken. Total charge is not broken, but the charge conjugation is broken. And you can also take instead of charge conjugation, you can take the parity. Then parity, what would be happen then? So just charge is not touch, the direction of motion changes, right? So initially, pion so initially we have this kind of situation. Helicity 1/2, helicity minus 1/2. But now after the parity transformation, mu1 goes to the opposite direction. Also, neutrino goes to the opposite direction, and the spin direction is untouched. So because of that, neutrino would be, so this is the mu1 plus neutrino. The neutrino helicity would be plus, and the muon, velocity of the anti-muon will be minus. So in this case, you can see that this one, and here on neutrino, velocity will be right-handed. So weak interaction, you don't see this kind of right-handed. So this is left-handed anti-muon is not observed. So because of that, also parity is violated. So this bottom line is the decay rate. We call the decay rate in particle physics. So decay rate is not the same when under the charge conjugation, and also decay rate even for the same cross charged pion, when the helicity is flipped, this process is not observed. So C and parity, both of them are broken. So if you combine C and P, then you can go one step further. So here, so starting from this configuration, and you apply charge conjugation in this scenario, then pi minus, mu minus. So you can just change particle to antiparticle, and but the spin direction is the same. So because of that, you can determine the helicity. 2 plus. So this scenario. So after C and P, that means the existence of a left-handed muon and anti-muon and right-handed anti-muon. So in the weak processes, again, so this one is observed. Because of that, we can say that it's almost equal. I think the CP is almost good symmetry. So it's not perfectly equal, but almost equal. This one. So CP is good symmetry. So slightly broken, but it's good symmetry. Okay. So the bottom line is the weak decays. The positive, anti-muon interact with the right-handed anti-muon, or sorry, the left-handed neutrino, or left-handed muon right-handed anti-neutrino. They participate. And weak interaction. Okay. Okay, and the charge and purity violated, and CP is a good symmetry. So this is the lesson that we can learn from the pion decay. So here, from the point of view of the left-handed spinors, here, so weak interaction, from the point of view of weak interaction, we have left-handed and this left-handed neutrino, right? So another thing is there is also similar analysis you can done for muon decay, but I'm not going to into the detail. Other than the same process can be driven by the weak interactions also. So this from this lesson, so this electron must be the left-handed, and this would be a right-handed. Of course, this this one is the right-handed, etc. You can assign particular chirality for each case. So initially, this one must be right-handed, something like that. And also in this case, this one, this one, this one, and right-handed. So so we processes including the neutron beta decay and muon decay, etc., etc. So we need we can describe them and the Fermi interactions. So below electroweak symmetry breaking. So electroweak symmetry breaking. The weak processes can be described by the Fermi interactions. So the interaction strength determined by this Fermi constant and then this day you there are two processes, but here let me focus on the charged current. This and also electron also muon partner. So then this product, oops. So this weak current, charged current, because it carries non-zero charge due to the electron, and then the weak decays described by this point interaction, because this is a space-time dependent quantity, and all the wave function evaluated at the same point. So this point-like interaction in space-time, the muon decays at a single point. Oops. So so-called Feynman diagram, you can draw this kind of Fermi interaction. So G Fermi, the G Fermi equal to 1.66 times G square. So this Fermi constant. So so this interaction, Fermi interaction is the it's like psi, and psi some structure. There's some structure here. So gamma matrix and gamma 5 with some structure. And you see that we know that the dimension of the field dimension is 2/3 for spinor. So the 4-point interaction composed of 4 fermions has dimension 6. So 3.5 times 4, the dimension 6 operator. And we know that Lagrangian is dimension 4 in natural unit. So we need to multiply some mass dimension, so one inverse mass dimension, 1 over m squared in the coefficient. So G Fermi, as you can see, this G Fermi constant has dimension of energy square, right? It's energy, 1 over energy square, and this is the same as 1 over mass in natural unit. So we have a correct dimension in the coefficient. So dimensional ground, we need to have some quantity with an inverse dimension square. And also another thing is that there's this is dimension 6 operator. We call this dimension 6 operator. Kind of we call this is irrelevant operator or non-renormalizable. And also another thing is that the structure. So gamma mu structure interaction has a structure. This structure, and this gamma mu is vector. We call the vector interaction. And the second part is the chirality operator. So when you have a gamma mu, it's a vector, and then gamma mu times gamma 5, then this is axial. So this is axial, and this is vector. So combination of vector and axial. So, but the minus sign. So this is minus sign. That's why this is blue minus A structure. And also this is, we learned that this is the projection operator. So because of that, you see electron 1 minus gamma 5, neutrino bar projection operator. So this project into the left-handed electron. So left-handed electron participate this interaction. We must a structure. Because of that, when V minus A structure implies that the maximal violation of parity. And also this renormalizability, dimension 6 operator is valid. There are two things. I mean, the one is good. I mean, this Fermi interaction is good for low energy. Low energy. You can identify the energy scale from this Fermi constant, energy scale. It is the energy if so if energy is smaller than inverse Fermi, below that scale, it is good description for low energy physics. But if energy is greater than this energy, then it's not a good description anymore. We need to include new particle in your theory. So we don't know whether what is the origin of this Fermi interaction. So experimentally, we have inferred that this structure V minus A is determined by experiment. But we don't know. We measure Fermi constant from the muon decay. The muon decay is most precise. I think the determination of the Fermi constant. So we know this kind of effective interaction below the Fermi scale. Beyond the Fermi scale, this is not a good description. We need to include a new particle. So that means the contact interaction must include kind of intermediate massive boson. So intermediate massive bosons means that so this contact interaction, point interaction. So the contact is the point-like interaction. So must be extended to this structure. This is another Feynman diagram. So the so-called this is the W boson. So kind of if you have enough energy, you are opening up this block into this extended diagram, and you start seeing a new particle which mediate for muon decay. The problem of this introducing massive. So this is massive because it's a short range interaction. It's almost point-like if you see it far away. But if you look close enough, then you are expanding this diagram from contact interaction to a kind of extended interaction. So this interaction are occurring at two vertices, so-called two vertices. And the problem is how to introduce massive gauge bonds. Massive how to introduce massive gauge bosons. Initially, gauge bosons are massless, and how to make gauge bosons massive. So those are standard model. This is a Higgs mechanism. Spontaneous symmetry breaking of acid2 cross U1 hypercharge. There are many issues actually when you introduce a massive gauge bosons without spontaneous symmetry breaking. There are issues like a unitarity and the unitarity violation, etc. But I'm not going to discuss. For the rest of like 30 minutes or so, let me discuss spontaneous symmetry breaking and Higgs mechanism. I think you're all familiar on the abelian case. So first, let me start from global symmetry and the breaking of U1 symmetry. So U1 global symmetry means we are transforming field by constant phase, alpha is constant parameter. That means this is the global U1. So then the U1, you can construct U1 invariant Lagrangian, which is given by this Lagrangian. And then phi modulus square equal to phi star phi, complex conjugation times phi. If mu square is negative, then the ground, we are looking for the ground state for which the derivative of field equal to 0. So we call the vacuum expectation value of field is constant. So in the vacuum, the equation motion tells you the Euler-Lagrange equation, so-called. When there is derivative vanishes in the ground state, that means the vacuum expectation, like vacuum expectation value of the derivative phi vanishes. That means you are allowed to have non-zero vacuum expectation value of field. It's a constant value. Phi is constant value. So then the equation motion tells you that there is no derivative terms, only you have a derivative of potential, which is 0 in the vacuum, ground state or vacuum. I'm interchanging the word between ground state and vacuum. So then the derivative of the potential is the potential is these two terms. The potential equal to v square y square lambda y to the fourth. So if you take the partial derivative with respect to phi, then you will get to lambda phi, which is 0. Of course, there's point phi equal to 0. Phi equal to 0 is also a solution, but unstable, because the the potential shape is something like this, right? So phi is a complex field. Let's take the profile of the potential along the real direction. Then the potential shape is looks like this. And the origin, this is unstable field. If field is at the origin, will roll down. So we are talking about these two. This is the ground state, or this one is ground state. But the ground state is everywhere if you're opening up, so imaginary direction of phi. So collection of the ground state, continuous. There's a continuous kind of infinite set of ground state around the valley of the potential. So around the valley of the potential. So this then you see this kind of Mexican hat potential. There's a continuum of ground state. So if phi is non-zero, so non-trivial solution to phi will be given by this continuum. Let me call this 2, V over square root of 2 into the I phi. So V is the kind of vacuum expectation value, and this alpha, sorry, alpha, I'm using the transformation parameter before. Let me call this beta. So beta. So beta direction, you are, this, all the vacuum are connected, the beta. So beta arbitrary phase. And then there is no energy cost, but even if you are moving around in the valley, you are free to choose any point along the valley, right? So then means there would be a massless boson appearing. We call this is Goldstone boson. So this is due to the vacuum structure. The vacuum structure tells you that there's some degeneracy, kind of degeneracy of vacuum. There is no unique choice of vacuum in this case. So that corresponds to some massless boson. So you can explicitly show that existence of Goldstone boson by making a perturbation around the vacuum expectation value. So perturbation means the wave plus certain perturbation. But you can take a small perturbation, but instead we can just parameterize the perturbation non-linearly. So non-linearly, because this is complex, right? This is complex. And then we are parameterizing the field in this way. So V is the V is the magnitude, right? This V is a magnitude, how far from the origin. And you change the radial direction by h as well as the angular direction at the same time. So both of them would be a space-time dependent. So they are field H and B. Those are real scalars, but we can take them to be perturbations. So when you expand the Lagrangian now, we are making some perturbation. Of course, you can treat the Lagrangian fully if you keep the infinite series of this infinite series. But in the low energy, you can ignore large perturbation focusing on small perturbation only, then there is no problem. So the Lagrangian, then you can just plug this ansatz, kind of ansatz. But if you expand them, then you have a real part and imaginary part, etc. So there's one-to-one. Let's say you can take ansatz, another ansatz like plus I. Let's say something like this one. You can take another ansatz. So still, we are interested in small field perturbation around the vacuum. So in this case, both H and A, they are thought to be small. But you can take this kind of Cartesian coordinate, kind of Cartesian, and this is polar coordinate. We choose this polar coordinate and put it in the Lagrangian. And what we get? So derivative. So then the first, what is important is the derivative. So when you take the derivative of this ansatz, then you have e to the IV over V. And the derivative operator will act on the second factor to give you IV into the IV, something like that. And you can take the absolute square, right? Then this phase is over factor, it doesn't contribute, and this turns out to be real, and the second term turns out to be imaginary, pure imaginary. So we have got the sum of the real square real part and the square imaginary part. Get this result, right? And the potential is potential was given by this expression, and if you put this ansatz back into the potential, then you will get this one. This one. So there is no sigma, this B field does not appear. It does not. In V. So if you make a perturbation, then the interaction effective Lagrangian will be, because we are interested in small perturbation. So kinetic term for B, so this is the kinetic term called the kinetic term for B field. Now you also expand them. There's some higher order interaction. So expand them. Effective interaction is now this one. And from this one, you also expand them and imposing the condition for V square, which is given by this one. So mu k is the negative, then the V square equal to minus mu square over lambda. And you will show that there's a linear term. H here is here also there. The linear term will go away, and you have only quadratic terms. So minus twice lambda V square or ta H square, and plus some interaction terms for potential, so H interaction, and also derivative, high order derivative interactions. Derivative interactions. the low energy, you see disconnected terms and mass term and interaction for H. And this you identify the coefficient of H square. So interaction means the H cube, H quadratic, right? But the no linear term. So linear term, H term vanishes. So there is no, you could in principle have a linear term, but the coefficient vanishes for this condition. So you know that you know that region because the if you have a linear term, then you need to define another minimum. So if you have a linear term, then the vacuum expectation value would be shifted. So by definition, you are in the sense that you are in the stable minimum. That means the linear term vanishes, and that guaranteed by this condition. And this is the mass term for H scale. So therefore, effective interaction, you have seen that massive scalar, massive real scalar, but the B field is massless. This is Goldstone. John? I wanted to discuss the Goldstone theorem in general. So, okay, you can discuss the Goldstone theorem, the existence of massless scalars, massless bosons, full generality. But here we discussed this breaking down of the U1 global symmetry. Then you have this massless Goldstone boson. This is problematic. So this is the low energy. We don't see massless scalar problem. Problematic. So full generality, you can show that a non-abelian
I'm sorry, but why Goldstone boson is problematic?
Goldstone boson, why is it a problem?
Yes.
Because of course, this is the there is no interaction other than Higgs interaction here. There's some interaction from here. You can see that H bound B square plus H square. So divide by V. You see the derivative interactions between Higgs and this new scalar. Then typically this Goldstone boson interaction strength is proportional to 1 over V. 1 over V square and derivative, so derivative interaction. But this Higgs. But if you have a global symmetry coupled to the standard model, then you have a Yugawa interaction. So there will be a problem. So in the standard model, for instance, the standard model, I mean, the Yugawa interaction is fixed by the gauge symmetry. So there is no room for global symmetry. But you can think about some global symmetry, additional global symmetry. I don't know how to. Is there any example? So suppose the lepton, let's say 2xw model might be because Weinberg will check action is considered. So the 2xw model is the Weinberg. I don't know, the spelling is correct or I don't know. It's CZ or Z, I forgot. This looks, I don't know this time. Check. I don't know. You can take, looks like a C should appear first and to model. So in standard model, we have a 1 Higgs, but here there's 2 Higgs. And impose some global symmetry. Yes. So U1 global symmetry. We call, so in particular this case, PQ symmetry. Then 2xw model, well, it's far advanced, but the mass is the electroweak scale determined by sum of the two, sum of the V1 square and V2. So this is V2, the wave of first one, second one, wave of the second doublet. In that case, we know that the standard model H1 and H2, there are extra. So H2 contains extra scalars. So when actually here the global symmetry and the standard model symmetry broken at the same time. So this is a U1. So because of this 2xw model, you break this two symmetry at the same time. The first symmetry is the gauge, it's the local symmetry. And the second is global. So if global symmetry is exact means the Lagrangian is invariant under the symmetry, then you have a Goldstone. So this is called Weinberg will check action. Then in this case, there will be a lot of problems because the interaction of this action is derivative interaction. But the suppressed by the weak scale. So this V, the sum of the valve is the V equal to 246 GeV. And this guy action couples to the standard model many ways, like interaction scale equal to let's say quarks gamma mu. So it's not gamma mu. Q. Also, you have a lepton. Similar interaction for lepton. So lepton interaction. Let's say electron. And even this also couples to some loop factor. Sorry. 4 pi. Some maybe you can ask later what this means, but these are nothing but action, photon, action, gluon interaction. So not only this interaction is for action, quark, action, electron. So all the interaction will appear because of the interaction of the second Higgs doublet. It doesn't have to be the second Higgs doublet. If we have an interaction to any of the Higgs doublet, then you will induce all these interactions. But the point is that this action is massless. Of course, this is massless at classical level. That it becomes massive and quantum level. Some Qcd effect. So Qcd effect, it receives non-zero mass. This is a kind of Goldstone version, but it's broken. Goldstone, when this Yuan symmetry is broken at the quantum level. Although this is massive, it's very light. It's like it's very light, and I don't actually. You can estimate. There's some whole discussion on the invisible action. You can make it visible instead. So then, if action becomes visible, then you have a problem. You have a meson decays, you can produce them, etc. The interaction scale is the 1 over V. So as I said, so this is you see that this is dimension 5 operator, right? This A is the scalar field, QQ bar, dimension, maybe this is the dimension 3, and derivative, so dimension 5 operator, right? So 1 over V, that means this is effective interaction below the symmetry breaking scale. But this V is very small. So because of that, this action, the Weinberg will check action is visible. Although it received non-zero mass due to some QCDs, but it's still very light and coupled very strongly because 1 over V. So in the case of invisible action, just to replace 1 over V by 1 over A, and then this A, instead of 200 something, this scale is the 10 to the 8 GeV and 10 to the 12 or 11 GeV. So this is the window for the invisible action, but this is the visible because the 1 over V, when for small V, you have a large interaction. So coupling is very large. So you are in a more danger. Yeah. So maybe it will be interesting to look up this one, but I think that this is one example to extend the standard model by including some global symmetry. But it failed, and later on people introduced some invisible action models. That's why people are excited about that. And still, actually, IBS kept the action searches, IBS, not ABS. They are looking for the visual action. But in this case, this H1 and H2 is not enough. So you need to add one more scalar. So this scalar is not the standard model Higgs doublet, but additional scalar. So then it will work. Is that the answer to your question, Song-sik?
I may understand what you mean, but okay. So yeah, I think.
So yeah, massless particle in nature, you don't see much. So you have photon, nothing else. It's massless particle with the sizable interaction will be dangerous. So because of that, the Goldstone, although it is nice theorem that shows the existence of new massless particles other than photon, it is in conflict with the experiment. So because of that, we wanted to find a way to evade the Goldstone theorem. So this Goldstone theorem can be generalized. This one is more on group theory part. So ON, I wanted to say about this one, ON group. I think that let me continue our discussion in the next lecture, although maybe we are keep postponing the real physics like Feynman diagram, etc. But I haven't taught much about group theory in the past particle physics lectures. Just let me summarize what are the groups, what kind of groups you can think of. So there are several candidates. Actually, I was about to tell you another group which may exist, and so non-abelian group, Lie groups. So as you remember, the Lie groups, kind of groups. Lie group means the existence of a generator, and then there must be infinitesimal transformations. So you can think of infinitesimal then you can match one-to-one between infinitesimal transformation and generators. So that is the definition of Lie group. Because if you find the generator for each infinitesimal transformation, then you can construct group made of generators and define the Lie algebra. Then that is the group, Lie group. So there are actually 4 A, B, I think the A, B, D, E. series. I don't know which one is which, but there are A, B, D, E. It's not A, B, C, D, A, B, D, E group. So the first one is the unitary. Unitary group is SUN. Of course, if in the case of UN, that contains U1 factor, but it's a special and unitary. In this case, special means determinant. Some transformation determinant equal to +1. And unitary means this quantity, this property. So from there, you can find that dimension of group is, sorry, not this one. Dimension of group is n squared minus 1. So that is the unitary transformation. Then what is the definition of the unitary transformation? Because you can think of certain object like and psi I and phi I, and then I runs 1 to n. You can think of this object, and then this take the conjugate one of them, and take the product, the sum. This is a sum, and this is invariant under SUN. There is group of unitary group, and there is condition U dega U equal to identity. This unitary transformation leave this combination invariant. So second is the orthogonal. So orthogonal SON. Of course, if you drop S, then ON. The difference is that let's say the transformation matrix O for SON, and the determinant of O equal to +1, and the O transpose O equal to identity. Transpose. Okay, so and ON, in the case of ON, the determinant, the transformation matrix can be either +1 or -1. So we are also including -1. So there is no big difference between these two cases, SON and ON, but there's a difference between SUN and UN due to the U1 global symmetry is included in the UN. And in the case of this -1, is the discrete transformation. So as I said, when you introduce new generator in the Lie group, you need to have an infinitesimal transformation. So in the case of discrete transformation, you don't have infinitesimal limit. So discrete, like a 90-degree rotation, something like that, right? So because of that, I think for the number of generators, this SON and ON, they are the same. Number of generators are the same. Okay. So then the dimension, number of generators or dimension of group is in both cases given by this one. Okay, you can count that, and the number of generators. This is the SON is the end rotation. If you think of rotation, in 3 dimension, n equal to 3, but the rotation group in D dimension. So SON. And third is the symplectic. So symplectic group is SPN, and N is even. In this case, what preserved is that you can take the same. In the case of orthogonal, I forgot to tell you, if you have this two set of field and take the psi I, phi I, instead of conjugate, you take just without conjugation. So then this combination is invariant. Then you have a SON invariant in symmetry. So in the case of symplectic group, you can construct this kind of product. Now you have a double sum here, I and J. And if this is invariant, so epsilon ij is a 0, 1, minus 1, 0. And this I is the n, so n over 2 times n over 2 matrix. So identity, so kind of block, and n over 2 times n over 2 blocks. So then this is invariant. Then let's say if you have a transformation, let's say this P, symplectic transformation, then this P matrix satisfies following condition. So if you satisfy this condition, it looks very similar to orthogonal group, apart from this epsilon. So epsilon equal to 1, then you have orthogonal. But this is different from orthogonal group because of this epsilon. And you can show that this transformation matrix P can be written as this block diagonal block form n over 2 times n over 2 block forms. So in all the A, B, C matrices are block forms, and you can impose certain conditions on A, B, C, D to satisfy this condition. Then you can find that the dimension of group for symplectic SP n will be where is the number 2 n plus 1. So SP. So remember that the n must be even SPn. And also maybe you can look up the some textbook, or maybe even you can Google. Maybe you can find the Wikipedia about this symplectic group, and so you can try to count the number of generators in this case. Then lastly, before concluding today's lecture, exceptional. So exceptional groups are G2, F4, E6, E7, E8. Okay, so 2, 4, 6, 7, 8. So this is the subscript indicates the rank of the group. As I said, the rank SU3 is rank 2. SU5 actually rank 4. And then SO10 rank 5, something like that. And then this rank, the meaning of the rank is the commutator, HI, some generators like a T, TI, TJ, they are commuting each other, but they belong to the group. they are commuting. And the number of T belonging to the group, that is the rank of the group. And this is rank 2, rank 4. Rank 2 means it is similar to SU3. Rank 4 is similar to SU5. And exceptional group is the larger rank. It's larger than so because of that, E6 is rank 6. So rank SO10 rank 5. So this contains SO10 plus U1. So U1 factor is the rank 1. Oops. So this is rank 5 and rank 1. So rank 6. So because of that, you can, when you think about exceptional group, then naturally you are thinking of grand unification. Then SO10, you see, includes SU5 times U1, and the SO10 rank 5 as this 4 and 1. The number of ranks is preserved. If you break, I mean, it depends on how to break the big group, but normally the rank is preserved. Because of that, the identification of rank is important. So then you can see that there's some sequential breaking of big group. And the standard model, let's say SU5 belongs to SU3 plus SU2 plus U1. And the SU5 rank 4. This is 2, 1, this is 1. Rank is the matched. So then you can see there's some sequential breaking of the big starting from E6. Then you end up with the standard model. Okay, so what about that? What about this E6, E8, E7? So E7, E8 you can think of. Then so this is similar to E6 cross SU2 because rank of SU2 is 1. This is 6. So E8 contains E6 times SU3. So this is 6, 2. So because of that, I think the E6 is enough in this picture. So E6 is enough for gauge coupling. If you unified gauge coupling means GS, G, G prime. So 3 couplings, those are unified. So then E6 is sufficient. But if you want to unify flavor the Yuga coupling, then you need to go to E8. So E8 belongs to so E6 times SU3 belongs to the E6 E8 group. So then that's why people discussed a lot about E8. And this is string theory. This is the big group you can think of. This biggest. Biggest gauge symmetry. It's called heterotic string. So this is the E8. We obtain standard model. E8 prime is the hidden So this is the picture that kind of people have accumulated for many years, like a past, I don't know, 40 years, something like that. And so this is like our current knowledge. And so in this case, the string theory can be defined strongly or weakly. So weakly coupled heteroscedastic string theory, you have this big gauge symmetry. So you can start from there. You can try to go down to the low energy, etc. So that's why I'm talking about this exceptional group. And I think that this is father group, and then all the Lie groups are related in a certain way, and they are related to the standard model, and they are related to the unification, etc. So, so next time we are going to discuss the take the simple example, because ON is easy to understand. This is orthogonal, so rotation in n dimensions. So we are going to discuss for spontaneous symmetry breaking and Goldstone. Sorry. Okay. But this is that I spent too much. Okay, this is end. So do you have any more question? If not, maybe you can.
I ignored it. Sorry.
Yeah, if you're interested in, you can try to find the structure constant. The structure constant you can calculate for Gelman matrices. And the Pauli matrix it is simple. SU2, SU3, it is simple. But what about other groups? You can also think about that. Also, exceptional groups. It's very exceptional, but those are important. And I think so. The so-called flavor symmetry. So this SU3, there's a 3, right? 3. 3 is a 3 generation. 3 generations, right? You have a up and down, and charm strange, and top bottom, and the leptons, right? These are 3 copies. So this is 3, stands for 3 identical copies of generations from unification. So you unify all the gauge interaction and Yugawa forces in these frameworks. So of course, in nature, they are different. So the problem is how to explain the differences between different forces. In the end, all the forces are unified. So this is a simple picture, but I also think this is very nice and good motivation to extend the group theory, the gauge structure of the standard model, and maybe dark matter. For dark matter discussion, I think that is based on 4 of these gauge groups. You can take dark gauge symmetry, but if you introduce dark matter arbitrarily without symmetry, then you are doomed. You don't know how to introduce new interactions. You are doomed. You don't know how to do. So once we have a symmetry, then you can construct the interactions in Lagrangian, etc. Then you can go forward and then find some implications, etc. So I think in this picture, there's some hidden sector. So hidden sector as large as the visible sector. Then there's nothing wrong to consider the copy of the standard model in the dark sector. And you can look for the dark standard model. So it'll be interesting. But I think okay, there are some issues, but we can discuss as we go along in the lectures. Okay. Okay, thank you for your listening and questions.